Momentum and energy. So I want us to start by the law of conservation of linear momentum. It states that total linear momentum of an isolated system remains constant. This means sum of all initial momentum is equal to sum of all final momentum. M1 V initial plus M2 multiplied by its V initial is equal to M1 multiplied by final velocity plus M2 multiplied by its final velocity, Vf. Elastic collision. If two objects collide, both the kinetic energy and linear momentum are conserved. This means the kinetic energy before collision is equal to the kinetic energy after collision. Also, momentum before collision is equal to momentum after collision. So if elastic collision occurs, there is no damage to objects because there is no loss of energy. In elastic collision, when two objects collide, only linear momentum is conserved. The kinetic energy is not conserved. This means kinetic energy before collision is not equal to the kinetic energy after collision. Some of the energy is lost as sound and heat. To prove elastic collision or inelastic collision, we only have to prove the kinetic energy is conserved or is not conserved. We mustn't use linear momentum, because we know linear momentum is conserved in both elastic collision and inelastic collision. Given an impulse and momentum question. The question reads: a soccer player kicks a ball of mass 0.45 kg to the east. The ball travels horizontally at velocity of 9 meters per second along a straight line without touching the ground and enters a container lying at rest on its side as shown in the diagram below. The mass of container is 0.20 kilograms. So this is the diagram before collision, where a ball have mass of 0.45 and its initial velocity. Also, the container have a mass of 0.2 kgs and is initially at rest, meaning its initial velocity is 0 meters per second. The question continues: the ball is stuck in the container after collision. The ball and container now move together along a straight line towards the east. Ignore friction and rotational effects. So this is after collision, where the ball and the container are moving off together with a common velocity, which is the V final Vf. 4.1. State principle of conservation of linear momentum. It states that the total linear momentum in an isolated system remains constant. This means the sum of initial momentum is equal to the sum of final momentum. So this can be represented by the equation M1 V initial plus M2 V initial is equal to M1 multiplied by its V final plus M2 multiplied by its final velocity Vf. Next question: calculate the magnitude of the velocity of the ball container system immediately after collision. So these ones, they are moving off with a common velocity, meaning both of these two masses, M1 and M2, they are moving with Vf. So our 4.2, we are going to modify our equation as this: M1 V initial plus M2 V initial. Since they are moving with common velocity, Vf is equal, so we rather factor it out. So by factoring out the Vf, we'll be left with M1 plus M2, then Vf is factored out. I'm taking M1 as the mass of the ball, then M2 is mass of the container. So our M1 is equal to 0.45 multiplied by its initial speed, which is 9, plus M2, which is 0.20 multiplied by its initial speed 0, is equal to mass of the ball, which is 0.45 plus mass of the container 0.2 multiplied by Vf. By simplifying on the left hand side, we get 4.05 is equal to 0.45 plus 0.2, which is equal to 0.65 Vf. Then we divide by 0.65 both sides, then this will give us Vf as 6.23 meters per second. 4.3. Determine by means of suitable calculations whether collision between the ball and container is elastic or inelastic. To prove elastic collision or inelastic collision, we are only allowed to prove with kinetic energy, the initial kinetic energy. The formula for calculating kinetic energy is half mv squared. So we calculate kinetic energy of the ball and kinetic energy of the container. But in this case, this container is at rest, so meaning its kinetic energy is 0, half mass of the ball, which is 0.45, and multiplied by its velocity 9 squared. This gives us 18.225 joules. Now let's see the final kinetic energy. It's half mv squared. But in this case, our mass is for the ball and the container. So we combine the two by adding 0.45 plus 0.20 multiplied by our common velocity that they are moving with at 6.23. This will give us 12.61 joules. So we can see that the initial kinetic energy is not equal to the final kinetic energy. Therefore, the collision is inelastic.